I'm Avi. I'm a PhD student at Monash, and I'm a member of the LIGO-Virgo-Kagura collaboration and OSGraph, which are two groups which try to understand the universe using gravitational waves. And so today I'm going to be continuing with what Renee was talking about, and I'm going to be talking about how black holes can be used as our snitches. We can use them to learn more about the universe now with gravitational waves. So first, I'll talk a bit about active galaxies and black holes, and then I'll talk about gravitational waves that come from inside these active galaxies. And then finally, I'll start talking about my research and how I use these black holes as snitches. So to start, I'd like to show you all one of my favorite astro pictures. So this picture here is called the Hubble Deep Field. So it was taken in '95. A year before I was born, but my dad had it printed out, and it was in my bedroom, so I kind of grew up with it. And it was taken in '95, and it was taken by staring at this one tiny small area in the sky for over 10 days. And so that area is the area that a tennis ball would take up if you threw it 100 meters above ground. So it's basically like a pinprick in the sky. And so after staring at that small space in sky for 10 days, they made this picture. And if you zoomed into this picture, you'd be able to see all these small points of light are actually galaxies. So there's over 3,000 galaxies in this small picture. It's pretty amazing if you think about it. What's interesting about these galaxies is that most of them are considered to be normal galaxies. Our galaxy, the Milky Way, is also a normal galaxy. But there's these others called active galaxies. And active galaxies are those which most of their light comes from the central region. In a normal galaxy, the light comes it's evenly distributed throughout the galaxy. And most of it is visible light, and it comes from the stars that are in the galaxy. But here in this active galaxy, most of the light comes from the central point. You also have this giant kind of jet that's coming out from both ends. And if we take a look at real pictures of such galaxies, so you have M33, that's a normal galaxy. And here you can see that it's diffuse a bit, and their stars kind of evenly spread out, so light's coming evenly throughout all the galaxy. And then you have M87. And so we saw this in Renee's talk as well. This was the famous black hole picture that was taken in 2019. And if we zoom into that central part, we see that we have something with the jet. And if you zoom in further, that's where we see our black hole. Now, would someone brave enough try to pronounce this black hole's name? Come on, someone. I'm gonna point at Evgeny.
Isn't emit or something?
No, the black hole's name. It's written.
Bowie?
So it's pretty close. It's pronounced. I'm also gonna try my best. I had to check YouTube. Bovehi, and it's a Hawaiian word, and it means unending source of eternal creation or something. Gosh, I should know this. But it's a really cool name, and it's a Hawaiian name because the telescope which pictured this they used a couple of telescopes in Hawaii, and there were a couple others which were all around the world, but they decided to go with the Hawaiian name for this guy. And this guy is known as a supermassive black hole. So it's a bit different from the ones that Renee was talking about. So Renee's primordial black holes could be very small, right? They could go up from super tiny, like less than a kilogram. And some of them could go really big, right? But these supermassive black holes, they're all just super big, right? They're so big that they sit in the center of their galaxy. And in fact, most galaxies actually have a supermassive black hole sitting in their center. Only difference is that in active galaxies, they're actually actively doing something to make stuff happen. And what they're doing is they're actively eating up gas, dust, and other stars that are nearby them. And so that's what we saw in the previous picture, that red glowing bit. I think Renee also mentioned this. That was the accretion disk. That's this part, right? That's what happens when you get gas too close to your black hole. It starts getting swallowed in. And the way this works is kind of similar to the way water runs down a drain in a bathtub, right? So you might see water is kind of like spiraling inwards, and the water that's further out is a bit slow, but as you go further and further in, it becomes faster and faster, right? Okay, so now I'm gonna try running a small experiment with you all. So I'm gonna get you all to put up your hand and place your other hand on top of it, right? Now start moving the top hand in a circular motion. Now move it faster, faster. Now, do you think you can get this to the speed of light? No? Okay, well, what was actually happening? Can someone tell me what was happening to your hand right now? Was there any change?
It's heating up.
Sorry?
It became a bit hotter, like heating up.
So she just said that it was heating up, right? So yes, it was heating up. Does anyone know why it was heating up? Friction. Yeah, so I heard friction in the crowd. So when gas starts moving in really, really fast, it starts spiraling in, what's happening is that it's rubbing against other gas particles, and this is causing friction. Friction is in turn causing heat. And that's actually why we see the accretion disk. That's actually why we see this active galaxy. This black hole is eating up all its food nearby. It's greedily eating all this stuff, and it's leaving a mess. All the stuff that's being left behind, I mean, all the food that's entering its mouth, it's basically creating a lot of friction. And that's what the light bulb is. So in this case, we have the supermassive black hole, which is eating up stuff in the accretion disk, right? And the accretion disk, as it rotates, it also has a magnetic field. And that magnetic field then can shoot out these particles in the form of the jets. So those are the different bits in the center of this active galaxy, right? And if we take a closer look at the supermassive black hole, so we have this guy lifting weights here. He's pretty big. He's pretty swole, right? And you have the other guy, right? So here, this guy is known as a supermassive black hole, and it is like millions and billions times the mass of our sun, right? And Pau Vehe, that was 6.5 billion times the mass of our sun. So pretty darn big. Now if we go to the lower end, if you go super far down, like even off my slides, we have those really tiny primordial black holes, the ones that Renee was talking about. And now if we move slightly up to about 5 to like 100 times the mass of our sun, we have what are known as stellar mass black holes. Now, these guys are heavier than our sun, right? But they're actually like radius, their size is actually smaller. So in fact, these guys would actually be less than 5% of like the. Okay, I think my slide might have been cut off. They're pretty small. They fit like within Earth. And we know how these guys form. These form when there's like these violent cosmic events that occur, such as when neutron stars smack into each other, or when stars blow up in a supernova. So when that happens, sometimes you're left behind with something, and that could be a black hole. Now, we have a lot of evidence for black holes from like 5 solar masses to even 150 solar masses, right? And now we also have evidence for these black holes, the one lifting weights right now. That's the one we took a picture of, Bauvehe, right? And we've also pictured the one at the center of our galaxy, Sagittarius A star. In fact, the Nobel Prize was awarded to it, I think last year. Andrea Ghez and I think 2 other people were awarded the Nobel Prize for their studies trying to figure out the supermassive black hole, the center of our galaxy. And that kind of leaves a big gap in the middle, right? So this area is a bit unknown. We don't know, why we don't really see black holes in this area. What's also unknown is how these guys form in the first place. So yeah, primordial black holes might be one way, right? If early matter in the universe kind of formed this big guy. But we don't really know other ways this could form. There are ways we know how the small guys, the stellar mass black holes, can become slightly bigger, and that's if they start eating up some gas and if they start eating up some stars, or also if they merge into other stellar mass black holes, so they can become slightly bigger that way. But the universe just isn't big and old enough for those guys, the stellar mass black holes, to have turned into these guys by just eating up other black holes and eating up mass. So we're pretty lost. But hopefully, looking at active galaxies could help us with this. Now it gets a bit tricky. Active galaxies, we have one perspective in our universe, right? We're in the solar system, and that kind of limits us. Astronomers have to struggle with this all the time. So right now, you can probably see I'm holding up a coffee mug that I stole from the physics department. Duncan, please don't tell anyone. All right. But right now, you can see the front, right? You can't see the handle. And as I rotate it, as I change the perspective, you can now see the handle, right? What's also interesting is if I change the angle slightly further, you'll see there's something hidden inside. There's a little chick, right? So that's kind of what we need to deal with as astrophysicists. We're in the solar system, and so that's kind of our perspective. That's the angle we have. That's kind of what we have to deal with. And so when we look out at space and we see active galaxies, we can see these guys, right? Sometimes we have the jet pointing straight at us. It's like right into our face. Sometimes we have it kind of angled, right? And that's kind of how we saw the M87 black hole Pavete. And it gets a bit tricky to study these in these different perspectives. What's also a bit frustrating sometimes is the fact that there is all this gassy stuff. We can't actually poke our heads in and stare at what's going on inside the gas. The same way when you stare up at a cloud, I don't know if you guys wonder, but I wonder this all the time. When I stare up at the clouds, I wonder, could there be a bunch of birds partying inside? I mean, I don't know, there could, right? We can't really see, we can't say no, but it's the same thing here. We can't really see inside these accretion disks of these active galaxies. And this is where my research comes in. Black holes, the stellar mass black holes that are inside these active galaxies, they can smash into each other. And when they do that, they start sending off these gravitational waves, ripples in this fabric of space-time. Those waves can eventually reach us, and with that, we can learn about these active galaxies. This is how we've made these black holes our snitches. They're snitching for us by sending us gravitational waves, telling us the secrets of these active galaxies. Now, to give you a better picture of what actually happens when these two black holes move, I have this animation made by the LIGO folks. So hopefully you all can see this, but here there are these two black holes moving, orbiting each other, and they're literally dragging around space-time with them. And they've merged, and these ripples are going. These ripples are like a cartoon illustration of gravitational waves. These gravitational waves are moving through everything, all of space. These are all galaxies, by the way. And eventually they reach our galaxy. Our galaxy right there, Milky Way. And they pass through Earth. So this is a bit exaggerated, don't worry. We're not actually being squashed and expanded like this sponge ball, almost, right? But that's kind of what it is happening. As the gravitational waves pass through Earth, it's contracting and expanding Earth itself. And we can actually detect this. So we have two detectors in the States called the LIGO detectors. The Laser Interferometry Gravitational Wave Observatory, that's a mouthful, that's what it stands for. Then we have the Virgo detector in Italy. We have the Kagura detector in Japan. We might, hopefully, be building one in Australia called NEMO, I hope. And we're currently in the progress of building one in India. And hopefully, soon in the future, we'll have one in space. But now to actually see what the data looks like, so once this gravitational wave passes the Earth, our detectors start recording the data from this. And if we were to plot it, it would look something like... Okay, so I don't know if you can hear that, but that's kind of what the sound this gravitational wave would make if it passed, if we played it as a sound. Right? So it's kind of like a... I don't know if anyone else can try to whistle that. So it's like a chirping increased sound, right? So if you look at this plot again, So that blue part is the signal, and the gray stuff is the noise that's just present in the data. Okay, so we have stuff out there in the universe with populations of these black holes. They smash into each other. They emit these gravitational waves. These gravitational waves eventually reach Earth. Now, this is where the astrophysicists come in. We kind of play this game of first trying to search and detect these gravitational waves that pass through Earth, right? Once that happens, we want to try to figure out, okay, now that we've found that this gravitational wave is here, what actually created it? What type of black holes? Like, what were the sizes of the black holes? Right? So we play this game of where we like listen to that song, that chirp, and we then try to like almost use software that's kind of Shazamming it. Have you all used Shazam? Have you ever like, you go somewhere, you don't know the song, you just click that button and it tries to like look through all the songs that exist to try to figure out what song it actually is, gives you the name. So we do the same thing, except for with black holes. So we use that to then figure out the sizes of the black holes. And then once we have a bunch of these black holes, we can start playing a game of trying to figure out where these black holes could actually come from, right? We could start looking at the demography of the black hole. I hope I pronounced that right. Demography of the black holes. So now this is kind of some of the work that I've recently published. I'm playing the role of a black hole paleontologist. So a paleontologist is someone who basically digs up dinosaur fossils, and with those fossils tries to figure out what dinosaur it could correspond to, and then after that tries to understand the environment in which this dinosaur lived. So I play that same game, but with black holes. These gravitational wave signals are sent to me. I then try to figure out the black holes that could have created it, and then once I have a bunch of these black holes, I try to figure out more about the active galaxies that they could come from. So here I have this like illustration of different types of active galaxies and the different type of black holes that might exist. So as you go up, you increase the density of your active galaxy. So it becomes thicker and thicker. So on the low end, you have active galaxies which are really thin. Black holes can run around freely, la-di-da, everyone's happy, right? But then as you go up, it becomes thicker and thicker, and it's almost like you're like running around in Vegemite. Would that be fun? I don't know. I kind of like Vegemite, but not that much, right? So it's a bit hard to move around in that region. Now on the bottom, you have black holes, going from active galaxies going from young to old. So on the left, everything is young. Sorry, yeah, you're left, right? Yeah. On that side, everything is young. Everyone's like partying, having a good time. Things are going crazy. And then as things get a bit older, they want to chill out. They want to just chill, right? And things are a bit more laid back. So what's happening with these black holes is that in the bottom region, where things are thin and the galaxy is young, the black holes are literally spinning in random directions. And as you go to the older and thicker case, everything kind of starts lining up. So does that kind of make sense? So this is kind of my model. This is the model that we're using. And with this model, we simulated a bunch of these different types of black holes. We simulated a set of these thick and middle-aged black holes. We simulated a bunch of black holes from an active galaxy, which was thick and middle-aged. And we also simulated one from like a thin and young active galaxy. Right? And we then kind of played this game of like almost, what is it? The sharks versus jets, where we try to compare the two sets of black holes. And we try to see if how many black holes we would need to start distinguishing if, hey, do these black holes come from an active galaxy from like a thick and middle-aged active galaxy, or do they come from a thin and young active galaxy? And so we saw that we need about 200 gravitational wave events, so 200 of these black holes smashing into each other, to start making these conclusions. And we're pretty close. Right now, the gravitational wave results so far, we've found 85 binary black hole mergers. So BBH stands for binary black hole. So we found 85 gravitational wave events from binary black hole mergers. And our detectors are going to be turning on pretty soon, at the end of this year, hopefully. And we expect that we'll actually get about 130 to 160 new binary black hole mergers. And so that's going to give us enough black hole mergers to actually start constraining these things about these active galaxies. Now there are a couple of other things on this. So we also have these BNS mergers, that stands for binary neutron star mergers. And we also have an NSBH merger, which is a neutron star black hole merger. And for those, we've only got a few, but we hope to increase those as well. And if you all want to actually keep on, on track of how many detections we made, there's actually a pretty cool app called Chirp, and it'll play that chirp sound every time we get a new detection. So if you're ever at the theaters and you hear a chirp, it's probably me forgetting to have put up my phone on silent, and yeah, but I would suggest getting it. It's kind of fun. All right. So in summary, our current view of AGNs is, it's a bit hard to study these AGNs, right? But we can now use black holes as snitches to help learn about these AGNs. And these black holes are personally sending us messages in the form of gravitational waves to tell us the secrets of these AGNs. I realized I said AGNs. AGN stands for active galactic nuclei. Yeah, sorry about that. But yeah, this is my research.
How many snitching black holes have you found, and what's one of the coolest things that it has told you about different black holes?
So when I say it's kind of a lie. It's all the LIGO collaboration, not just LIGO, but like the international, so it's like thousands of people, and I'm just one of them helping a bit. Yeah, so we found 85 of these binary black hole mergers, right? So that means we found 2 times the number of black holes separately, and they merge together to form a third black hole. Does that kind of answer your question?
Is that one of the coolest things that has kind of like told you about black holes, or the communication aspect between?
So those merging black holes will tell us, when those black holes merge, they'll be able to send out these gravitational waves, and then we'll be able to use those gravitational waves to then start studying things like where these black holes could have come from, and learn about the active galaxies that they could have come from. So people till now have been more looking at things like the overall spin properties of these black holes and stuff like that. And then with that, they can try to say if, do these come from things known as globular clusters, or are they mostly just found isolated in space, not like in any galaxy, but just like chilling around out there. So this has been the first, I think, study in which we've tried to map out if we can use these black holes to snitch on active galaxies.
Yeah, bonus related question. What is the funky little +1 question mark? Is that one that's reason or one that's heavily disputed?
Yeah, so as I played like in a couple slides back, the data we get is pretty limited, right? It's just that, right? And so when our Shazam app isn't that good yet, basically. We're trying to figure out like the best ways to actually try to mitigate all the noise and try to pinpoint exactly what it is. But sometimes it's a bit uncertain, and so that's kind of when this plays in. We don't know if that the +1 is because between this guy and this guy. So one of them could have been a neutron star. We're not sure if it's a neutron star or a black hole. Emily?
I probably missed this, but what actually is an active galaxy?
An active galaxy is just one of those in which the supermassive black hole is just like eating up a lot of gas and stuff nearby. And because of that, it's, the accretion disk is so bright that you can actually see it. And in active galaxies, most of the light comes from the nucleus, the center, whereas in normal galaxies, most of the light comes from like all the stars, and it's evenly distributed. So our galaxy is a normal galaxy, even though it has a supermassive black hole in the center.
So this is a follow-up to that one. Can you detect gravitational waves from inactive galaxies as well? And is there a way to distinguish between active and inactive?
Yeah, sorry if I misled anyone, but gravitational waves can be detected whenever these black holes or anything with a large enough mass kind of like moves around and then maybe smashes into each other. And so the detectors on Earth are currently geared towards sensing a certain frequency range of these gravitational waves. And the ones that we've been picking up so far have been from black holes smashing into each other, and specifically stellar mass black holes. So it's like the first detection that we saw was from two black holes of like 30 times the mass of our sun smashing into each other. And the largest gravitational wave that we've recorded has been from two black holes that ended up forming another black hole that was about 150 solar masses. But yeah, these aren't necessarily from active galaxies. They're literally just from any, black holes that could be smashing into each other. And I'll also highlight that right now, we don't know if, we don't know exactly where these black holes could be coming from. We actually think that most of these black holes are coming from isolated space. So not actually in any galaxy. Like just chilling out there, like alone in space. And this is partly because whenever black holes smash into each other, and firstly, they become bigger. Secondly, they also release some of this energy in the form of gravitational waves, right? And when that happens, they almost get a kick. They literally get a kick out of where they were. So they start moving, and sometimes the speed at which they're moving is fast enough for them to escape or like jump out of the galaxy that they're in, if they're in a galaxy.
Is that why there's a chirp, because they're moving?
So the chirp, maybe I'll play the video again. So in this slide, you can see that these gravitational waves are being emitted, right? And you see at the very end, the number of waves has increased a lot.
So you get
Yeah, the higher frequency comes because you have a lot of those wavefronts towards the end.